Hi guys, we're going to continue on with our types of collisions. I also want to do some examples with collisions and using some of the formulas that we're about to get to for elastic and inelastic. Just to kind of review a little bit, yesterday we talked about a new term called impulse. And ultimately, impulse just has to deal with an external net force that's acting on a system in a specific time interval. So impulse we symbolize with this symbol I, and I is equal to, especially if we're thinking about an average force, then it's going to be the sum of those forces in a time interval. So sum of the force times delta t. We know that impulse has similar units to momentum, and that would be kilogram meter per second. We also talked about yesterday that there's a new theorem called the impulse momentum theorem, and that is that impulse is equal to the change in momentum. So we know that the change in momentum is just simply my final momentum minus my initial momentum for a system. And yesterday we also, I think the last thing we got to were about the two different types of collisions. So we have an elastic collision and we also have inelastic collisions. In elastic collisions, we talked about how we have conservation of momentum, or momentum will always be conserved. In an inelastic collision, momentum is also always going to be conserved. So momentum must be conserved in all collisions. We know that in an inelastic collision that we have some kinetic energy is going to end up being lost, and that could be to sound, that could be to heat, that could be to matter transfer if we're thinking about a car, and then like the bumper gets taken off by the other car. So in an inelastic collision, kinetic energy is not conserved, but momentum is. And in an elastic collision, kinetic energy and momentum are both conserved. Okay, so let's talk about a perfectly inelastic collision. The momentum of an isolated system we said is conserved in any collision. So the total momentum before the collision must equal the total momentum of the system after the collision. Remember we said that an individual particle's momentum may change, but this, if I'm thinking about both of these particles as a system, then together their momentum as the system should remain constant. Now, we know that objects in an inelastic collision, in a perfectly inelastic collision, they will stick together. So I have mass 1 and mass 2. They're moving towards one another. They're going to collide. Ultimately, then they're going to stick together, and then they're going to move together with the same speed, with the same velocity. So because of that, I can think about, I know that before, let's say here's the mass 1, so the momentum of this particle would be mass times that initial velocity for this first mass, so m1 times v1 initial, plus, so if I'm thinking about, this would be thinking about the initial momentum of my system here. So I have this mass, this particle, but I also have this mass moving towards mass number 1. So I'm going to have the mass of the second one times the speed then, or the velocity of this particular mass initially. And this should equal my final momentum, which I only have to deal with one velocity here because they're moving together. So final, it should be both of the masses added together times that final velocity, because both of the masses are stuck together and now they're going to move together with the same velocity. So for a perfectly inelastic collision, m1 v1 initial plus m2 times v2 initial is going to equal the combined masses times their final velocity. Now, a lot of times in these problems, we always want to calculate this. That's a common problem for physics, is finding the velocity of the particles as they're moving together after the collision. So if I rearrange all of this, let me get rid of this and we'll just write it as the rearranged version. Then my final velocity for an inelastic collision should be my m1 v1 initial plus m2 v2 initial over the combined masses m1 plus m2. So again, this is just the only reason, it's the same thing as the last formula, but I'm just writing this out because you'll be using probably this one a lot. And I will add this to your Quizlet, so this formula will be fair game. So how to find the final velocity for a perfectly inelastic collision, I would expect that you would know how to do that, or that you could be able to derive it to either one. Now in an elastic collision, we know that both momentum and kinetic energy are conserved for an elastic collision. So for an elastic collision, I know that I'm going to have two masses that are colliding with one another, and they both have an initial velocity. They're going to bounce off one another, and they're going to move back in opposite directions in from when they collided. And then I'm going to see that they're not stuck together in this case, so they have separate final velocities. So in this case, I would have m1 v1 initial plus m2 v2 initial. Actually, let's rewrite this so I can make it a little smaller so I can get it on the same line. So m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. So this would be true for my conservation of momentum for an elastic collision. Kinetic energy is also the exact same thing. So I would say for my kinetic energy, well, let's go back to here. This would be my initial momentum here, and that would be my final momentum here. So they're conserved because initial should equal final. For kinetic energy, I know that the initial kinetic energy should equal the final kinetic energy, and I know that kinetic energy is 1/2 mv squared, so I could say 1/2 mass 1 times the initial velocity of the first one squared plus 1/2 mass 2 times the initial velocity of 2 squared equals all of this, same thing, but just the final version of that. So usually when we have an elastic collision, we're missing two pieces of data. So usually we need both of these equations, so then that way we can solve for the variables that we're missing. Okay, so let's, for example, look at an 1,800 kilogram car stopped at a traffic light, is struck from the rear by a 900 kilogram car. So I have this big, massive 1,800 kilogram car, and it is hit by a 900 kilogram car from behind, and it says the two cars become entangled, and they move along the same path together as this originally moving car was. So this car has an initial velocity of 0. The 900 kilogram car, it says, has an initial velocity of 20. So VI here equals 20. Should be kilograms, and then that's meters per second. Okay, we want to know what is the velocity of the entangled cars after the collision. So cars are going to be moving this way. Ultimately, I know from that rearranged equation that we just looked at for inelastic collisions that the final velocity should be equal to m1 v1 initial plus m2 v2 initial over m1 plus m2. Okay, so let's say that M1 will be the first mass can be my 900 kilogram car. So this is number 1. And let's say number 2 will be my 1,800 kilogram car. Okay, so I know that my second, this number 2, had an initial velocity here of 0. So the initial velocity here is 0. So that means this whole thing now is taken out. So really my final velocity is dependent on this mass of the first one initially, and then over the two masses together. Well, I know the mass of this first car was 900. I know the initial velocity of that was 20. We can consider it moving this way in a positive direction, so I can leave that velocity, this 20, positive. And then I'm going to divide that by 900 plus 1800. That will get me my final velocity. If we do that, we should get 6.67 meters per second. Okay, one of the last collision examples that I kind of want to do, because I think this one is going to combine energy methods as well as momentum, so this is going to be kind of a bigger, beastier problem. It says that a projectile of mass m1 is fired, so I have a bullet here, it looks like a bullet. So we have a bullet is going to be fired into a large block of a wood mass. This is also just called a ballistic pendulum, and that's just a way, it's an apparatus that we can use to measure the speed of how fast a moving projectile can move. So I can measure how fast this bullet will move based on having this, what we would call ballistic pendulum. So I have a bullet, a mass 1, it's fired into a large block of wood, and we'll call that mass 2. It's suspended from some light wires. Let's assume that these wires, their mass is negligible. The projectile, this bullet, is going to lodge itself into the wood. So now, once this bullet enters into the wood, it's going to move together. So this would be an inelastic collision because these masses are now stuck together. And once that projectile embeds in the block, the entire system is going to swing up a specific height, which we'll call h. We are asked, how can we determine the speed of the projectile from a measurement of height? So I want to know, what is this? What is the initial velocity of the bullet before it comes in contact here and it embeds in the block? And I want that also to have something to do with the height that the two masses will move together with, or move together through. Okay, well, let's think about a couple of things that we know about inelastic collisions first. So the one thing that I know about inelastic collisions is that once this bullet embeds in the block, they're going to move together. So their final velocity is going to be the same. So I could say that my final velocity of both of them together, because the two masses will be together, will be the mass of the bullet times the initial velocity of the bullet over the mass of the bullet plus, we'll say, the mass of the wood. Well, now, before in the last one, we said that the final velocity would be the mass of the bullet times the velocity of the bullet initially plus the mass of the wood times the velocity of the wood initially. But this block of wood, before the bullet strikes it, is at rest. So that means that this block's initial velocity is 0. So the reason that I didn't include this part was because this is just equal to 0. Okay? So let's go back. I'm going to erase this to simplify it down for us a little bit. So I know that the final velocity of both of these together is going to be this, the mass of the bullet times the velocity of the bullet initially over the two masses combined. So that's one thing that I know. Another thing that I know is that I could write an equation for the kinetic energy of the system. And if I do that, we know that kinetic energy is simply equal to 1/2 times the mass times the velocity squared. So ultimately, 1/2, I know the mass though is going to be the mass of the bullet and the block together. So 1/2 mass of the bullet plus mass of the wood together times v squared. Well, if I'm thinking about the amount of kinetic energy that it's going to have, I know that ultimately, when this bullet comes in here and they're moving together at a certain velocity, I know this velocity is this final velocity that we just wrote up here. So I want to substitute this in for V right here for kinetic energy. So let's do that. So I would have K equals 1/2 times the mass of the bullet plus the mass of the wood. And then I want V, which is all of this, mass of the bullet times the velocity of the bullet initially over the mass of the bullet plus mass of the wood. Yes, please. All of that is squared. Okay, well, ultimately, let me just say, I know this is squared, I know this is squared, so I have mass of the bullet plus the mass of the wood, and then I have the mass of the bullet plus the mass of the wood squared. So this one can cancel. I'd be left with just one of these. Now on the bottom. So that would simplify down to, let's go up here, guys. I'm sorry that it's like so incredibly messy. So I know that this would be K equals 1/2 MB VBI, so the mass of the bullet times the velocity of the bullet initially, that's squared, over mass of the bullet plus the mass of the wood. And then instead of just saying the 1/2 here, let's just go ahead and say, I mean it's 1/2, well, let's just say that this is 2, so it's 1 over then the 2. So my kinetic energy then of this entire system is equal to the mass of the bullet times the initial velocity of the bullet squared. Let's actually, this whole quantity is squared, guys, sorry. And then over 2 times the masses then collectively. So this is just stuff that we know. The reason that I'm writing all of this out is because ultimately our goal is to write, our goal is to get this velocity of the bullet initially. I want to get this term to equal something, but also in terms of height. So our bell is about to ring for our fire drill. We're going to pick up with finishing this up tomorrow. Bye!